So hi guys, welcome to the session. So in this session we are going to see the previous year questions of the UGC NET Electronic Science. So before going into the session, one announcement is that actually the UGC NET Electronic Science this June 2020 exam is going to conduct on 5th November 2020, that all of you know. So based upon that one, here the Unacademy is providing the crash course for the electronic science candidates. So it is the course is titled as Crash Course on Electronic Science through Multiple Choice Questions. So actually this course is going to start from October 1st onwards, and by the end of the month of October, this course is going to be finished. And in this course, all the 10 units, the topics will be discussed in brief, and the discussion of the topics, that means while coming to the formulas point of view or important topics point of view, and the question, okay, how they are going to ask the questions. So based upon that one, this course is completely designed, so which will be very much helpful to the UGC NET Electronic Science June 2020 applicants to crack the UGC NET JRF category. Okay. And if you are using the code, that is Aswini K, then you are going to get the 10% discount on any one of the subscription plans that I am going to show you the subscription plan right now. So apart from the crash course, if you are preparing for the December 2020 or for the June 2021 like that, then the Unacademy is providing a very good opportunity to the UGC NET Electronic Science aspirants. If you want to get the complete course, that means whatever the UGC syllabus is there, if you want to get the complete video lectures of that UGC NET syllabus, then the Unacademy is providing the complete course for that one. And if you want to take the subscription plans, so here the different subscription plans are there. That is for 1 month, 3 months, 6 months, 12 months, and for the 24 months. So depending upon at which month and which year you want to write the exam, so based upon that one, you may take the any one of these subscription plans here. And the highlights of this subscription plan is that you are going to get the live video classes, and you can clear your doubts at the time of classes going on. And after completion of the class, if you are having any queries or the doubts, then for each and every 3 classes, one doubt clarifying session will be there. So in the doubt clarifying session, you may ask your questions or queries through the text format or through the PIC format. Okay. So this, I mean, and weekly quizzes will be there, and the monthly quiz will be there. So a lot of opportunity and the flexibility is there through this Unacademy subscription plan. So if you want to get any one of these, I mean, subscription plans here, then you may use my referral code, that is Aswini K, to get the 10% discount on any one of the subscription plan. Okay. Fine. So now we will go to the main content of the video, that is the previous year questions. So it is a previous year question part 3. So in the part 1 and part 2, we actually discussed about the few questions. So these are the questions, and if you want the solutions of this one, you may go through the recorded videos, guys. Okay, in this YouTube channel itself, you will get the recorded videos, so don't worry. Please go through the recorded videos. And coming to the present session, we're going to start with this question, guys. Okay. Fine. So coming to this question here, so it is a question number 1 for this session. The question is, for an RC phase shift oscillator, the following statements are cited. Okay, RC phase shift oscillator. That means generally we are using the feedback ins. Okay, So feedbacking means why? Because the oscillator is the concept comes from the subtopic of the feedbacking thing. So while coming to the feedback, the two different types of feedbacks will be there. One is the negative feedback and the second one is the positive feedback. So based upon the source signal and the feedbacking signal, the phase shift difference between both these two, the type of the feedbacking is going to be decided. So that means based upon the phase shift difference between the source and feedback signal. Okay, fine. So coming to the negative feedback, if you are providing the negative feedbacking, then it is a very good thing to design the amplifiers, because even though the gain is less in the negative feedbacking concept, but we will get the stability of the gain. Okay, the stability of the gain is very much important in the case of the amplifiers. Now while coming to the positive feedbacking, the positive feedbacking is a very good thing for the case of oscillators. Okay, so oscillators are using the positive feedbacking. Okay, fine. Now we will see. I told that the phase shift difference between the source signal and the feedback signal, the negative and the positive feedback is going to be decided, right? So if the phase shift is 180 degrees, then it is called as a negative feedbacking. And if the phase shift is 0 degrees or 360 degrees, then it is the positive feedback. Okay guys, so it comes under the positive feedbacking. Fine. So these are the two different types of feedbackings will be there. Okay, anyhow, out of this 180 degrees, okay, so here I am telling right now that 180 degrees how we will get, and the 0 and 360 degrees how we will get in the case of the oscillator. Okay, so just have a look on this one. In the case of amplifiers, we'll take, it is amplifier. If it is a BJT, let's take the CE configuration, and here we will take the feedbacking part and it is a feedback. Okay, so it goes like this, and it is a source signal and it is a feedbacking signal. Okay, fine. So here in the case of the amplifiers, the CE amplifier itself will give the 180 degrees phase shift, and the feedback signal, okay, this 180 degrees phase shift will comes here, and the feedbacking network gives the 0 degrees phase shift. Now the 0 degrees plus 180 degrees, it will goes like this. Now the total phase shift difference is 180 degrees between the source signal and the feedbacking signal. Okay, so it is the case of the negative feedbacking concept, or else the case of the amplifiers, right? And the feedbacking network, whatever the circuit we are connecting in the place of the feedbacking part, here that network is giving the 0 degrees phase shift. 0 degrees phase shift is given by the which type of elements, guys? It is going to give by the resistive part. But because while coming to the capacitor and inductor, they will give the 90 degrees phase shift. Okay, and there is the leading and lagging between the voltage and the current in the case of the inductor and the capacitor. But if you have to get the 0 degrees phase shift, then definitely you have to use the resistors. So in the case of the negative feedbacking concept, your feedback network must be resistive network. Okay, fine. Hi Nasima, good afternoon. Fine. So it is a case of the amplifiers. And now, while coming to the oscillators, so in the case of oscillators, same, we will take the amplifier, we will take the feedbacking network like this, and it is the positive feedbacking. That means, as I told, that if it is a source signal and it is the feedback signal, it is the feedback network, and the phase difference between the source signal and the feedback signal must be 360 degrees, or else we will call it 0 degrees also, not a problem. So here, as I told, that if it is a CE configuration amplifier, then it will give the 180 degrees phase shift. Okay, but if you want to get the 360 degrees phase shift at this point, then the feedback network also has to show the 180 degrees phase shift. So now this 180 plus 180, both these two will becomes as a 360 degrees phase shift difference between the source signal and the feedbacking signal. Okay, so if you want to get the 180 degrees phase shift from this feedbacking network, then definitely it must be, it must contain either inductor or capacitor must be there. Okay, so that's why this type of feedbacking networks are called as a reactive network. Okay, so that means that in the positive feedbacking case, in the positive feedbacking case, what we are getting the 180 degrees phase shift through the feedbacking part. So if you want to get the 180 degrees phase shift, then you have to connect the reactive network. Okay, we have to get the reactive network. Fine. So it is a major difference between the amplifiers and the oscillators. In the case of the resistive network, in the amplifiers we are using the resistive network, and while coming to the oscillators we are using the reactive network. Fine. So now, after going through all these things, now what is the correct answer, guys? Here, what is the correct answer for an RC phase shift oscillator? The following statements are true. Amplifier gain is negative. Amplifier gain is negative. Of course, okay. Of course, in the oscillators, whatever the amplifier we are using, the amplifier gain is negative. But because if the amplifier gain is negative, then the CE amplifier is doing the 180 degrees phase shift. Okay, fine. Akshay, please once refresh. Okay. So the amplifier gain is negative, of course it is correct. And coming to the phase shift introduced by the feedbacking circuit is 0 degrees or what's 360 degrees. So it is not the correct thing. Why? Because the phase shift introduced by the feedbacking network is 180 degrees. Fine. And amplifier gain is positive. No, it is wrong. And the phase shift introduced by the feedback network is 180 degrees. So both these two are correct. That means A and B, both these two are correct. So here the third option is the correct one. Okay. The third option is the correct one. Is it clear, guys? Is it clear to everybody? Yeah, Taruna, if you are having both the two exams on the same date, then please check yourself. If the timings are different, then try to manage to write both the two exams. If the same timings are there, then that depends upon your priority. Taruna? Next, second question. So what is the output voltage V0 of the following circuit? Okay. So it is operational amplifier is given. So we have to find out the output voltage of this circuit. Fine. Okay. So to find out this one, first of all, we have to know what we call few ideal characteristics of the operational amplifier. Especially, we have to know about the virtual ground concept. Yeah, hi Akshaya, I am fine. I am fine, thank you. Virtual ground of operational amplifier. Okay, so first we have to know the virtual ground. Virtual ground means whatever the voltage we are connecting to the inverting terminal, and whatever the voltage is there, that means let's take it is a inverting terminal and it is a non-inverting terminal. Okay, so the voltage at the inverting terminal and the voltage at the non-inverting terminal, both these two becomes equal. Okay, and it is the case you have to take in the ideal operational amplifiers. Okay, fine. So usually, yeah, Akshaya. So both these two will becomes equal. Fine. So why we are taking as a equal in the ideal case? Because so if you are taking an operational amplifier like this, minus and plus V1, V2, and if it is a V0, so usually we are going to take the V0 is equal to gain into V2 minus V1. Fine. So from this case, V0 by A becomes is equal to V1 minus V2. So in the case of the ideal operational amplifiers, we will take the gain is infinity. Okay, we will take the gain is infinity. So here, if I substitute infinity in this place, then this entire term becomes is equal to 0. So now what I will get from this equation, I will get V1 minus V2 is equal to 0. That means V1 is equal to V2. That means the voltage at the inverting terminal and the non-inverting terminal, both these two will be same in the case of infinity or else in the case of ideal operational amplifiers. Okay. So whatever the problems you are getting like this, when if they are not given any type of gains, okay, then you can take the infinity as a gain. For example, if they mentioned the A is equal to 20,000 like that, then you have to substitute the given value in the case of such type of problems. Okay, fine guys. Okay, now we will solve this question, guys. So here the VA voltage is given and here the VB is given. So I am taking here the V1 and here also V1 at both these two nodes. So because as I told that the virtual ground concept, both these two voltages becomes equal, and whatever the current flowing through this 20 kilo ohms, the same current also flows through the 100 kilo ohms. Okay, and at this point V0 is there. But because whatever the current flowing through this one, that becomes is equal to 0 amperes due to the infinity input impedance of the operational amplifiers. In the same case, the current flowing through this 20k and through this 20k, both these two becomes equal. Okay. So based upon these things, now we have to write down the equations. So the first equation, the current flowing through this 20 kilo ohms can be taken as VA minus V1 divided by 20k is equal to V1 minus V0 divided by 100k. Okay, and 5 times will be cancelled, and if I do the cross multiplication, then I'm going to get 5VA minus 5V1 is equal to V1 minus V0, and 6V1, that means just bring this one here. The 6V1 is equal to 5VA plus V0. Okay, so let's take it as the equation number 1. Fine. And next, so coming to this VB, okay, whatever this direction I given here. So if we wrote the equation to this one, then what we will get? VB minus V1 divided by 20k is equal to V1 minus 0 divided by 20k. So both these two gets cancels, then I will get VB is equal to V1. Yeah, Akshaya, fine. So VB is equal to V1, and V1 can be written as a VB by 2. So let's take it as the equation number 2. That is V1 is equal to VB by 2. Okay, I am just substituting here V1 as a VB by 2 is equal to 5VA plus V0, and both these two here gets cancels. Now finally V0 becomes is equal to minus 5VA plus 3VB. So it is a final answer, minus 5VA plus 3VB. So the fourth option is the correct one. Fine. So it is the second question. And coming to the third question. So the third question, in a JFET, the change in drain current is due to applied. So that means whatever the drain current is there, the generally expression we are going to take as IDSS into 1 minus VGS divided by VP whole square. Okay, so it is the expression, guys. And VGS represents the gate to source voltage. That means if you observe, the drain current is depending upon the voltage what we applied between the gate and source. Fine. That means it is a electric field. Okay. So whatever the drain current we are going to take, it depends upon the gate to source voltage. Okay. So at the same time, the ID is also depending upon the source and drain also. Okay. Same time, it is also depending upon the source and drain also. Fine. But here, anyhow, it is not depending upon the magnetic fields. It has to depend upon the electric field only. Here they given that electric field between the source and drain and electric field between the gate and source. So in between the gate and source, we will be having certain type of potential difference is going to be applied. Okay. So the actual drain current can be controlled by the electric field between the gate and the source. Okay. By the gate and the source. So for example, if you are taking like this, it is a drain and it is a source. JFET means the construction will be like this. So this one we are going to take as a gate and it is a source. So coming to the voltage connections, we can connect in between the source and the drain. We'll connect like this, and in between the gate and the source also. Actually, we will reverse bias this one. Right? If it is a N channel, it is a P type. So actually, we will reverse bias this one. Of course, the change in the drain current can be bring due to the VDS and also due to the VGS. Both these two is possible, but most possibly it depends upon the electric field between the gate to source. Okay. Why? Because if you are increasing the more VGS, then automatically whatever your VDS it might be, the source to drain current becomes is equal to 0. Okay, and at which drain current, at which gate to source voltage the drain current becomes is equal to 0, that is called as a VGS off. Okay, that is called as a VGS off. So it is mostly depending upon the gate and source. So the correct option is the B. Next, how many flip-flops are required to build a binary counter circuit to count from 0 to 1, 0, 2, 3? That means totally how many counts we can do here? Total 1024 counts we can do. So 1024 counts means 1024 is the maximum min. Actually 1023 is the maximum count. How many bits we require? How many bits we require to represent the 1023 or 1024? Okay. So actually we have to take the count including the 0. That means 0 is also one count. So total 1024 counts it has to do. So 1024 counts means it becomes is equal to 2 power 10. Clear guys? It becomes is equal to 2 power 10. Yeah, Akshaya. So that means total 10 number of flip-flops will mean required to count the 0 to 1023. So here the correct option is the 10 number of flip-flops will require. Next. Two power n is enough, Akshaya. 2 power n we can take. Okay. And if you are going to the different counters, then the number of flip-flops are going to be changed. Different counters means just like the Johnson counter and coming to the ring counter. Okay. Next, when op-amp is used as an integrator, the feedback element is, when op-amp is used as an integrator. So first of all, integrator is nothing but a low pass filter. Okay, of course we cannot say completely that the integrator is a low pass filter. If one condition is satisfied, then the integrator is acting like a low pass filter. That condition depends upon the input signal time period and the time constant of the integrator circuit. Okay. So anyhow, low pass filter means we can take a resistor here and we can take the capacitor here. So it is a low pass filter. Whatever the input signal we apply here, and it is the output signal. So usually the capacitor allows the high frequency signals. That means all the high frequency signal will be grounded. Okay, and only the low frequency signal will be obtained at the output side. So it is called as a low pass filter. So while coming to the integrators, the same case we are going to follow here. We will take the like this. So it is the input and it is the output, and V0 can be taken as a -1 divided by RC into VA of t into dt. Okay. That means in the capacitor we are going to take the as a case of the integrator, the feedbacking element is the capacitor. Okay. That means this circuit can be represented like this. Why? Because anyhow here it is grounded, so that means here also the virtual ground concept will be applicable. That means the capacitor one end is connected to the V0 and the other end is connected to the ground here. Okay, so that's what low pass filter require the feedbacking element as a capacitor. Right? And if they told you instead of the integrator, if they ask you the practical integrator, okay, practical integrator means we have to connect one resistor in parallel with the capacitor. Okay, that option must be there. Resistor in parallel with the capacitor. Okay, but as if right now for this question the option B is the correct one. Fine. Next, del square V is equal to minus rho by epsilon represents what? What is this equation represents? Is it a Maxwell equation? We're having the 4 different types of Maxwell's equations, right? So we will get the 2 equations from the electrostatics and the 2 equations from the magnetostatics. So is it any one of that one, or else the Laplace equation, or else the Poisson's equation, or else the Gauss law? So which one it is? Any idea, guys? So coming to the Maxwell's equations means in the free space, we can write that del dot D is equal to rho V. It is a Gauss law and it is also one of the Maxwell's equation. Okay, and so coming to the Laplace equation, we will take the del square V is equal to 0. That means in the charge-free region means the rho becomes is equal to 0. Okay, so Laplace is also one of the case of the Poissons. If you take the charge-free region, then the Poisson's equation converts into the Laplace. Okay, so out of all these things, the correct option is the the correct option is the C. It is the Poisson's equation. So by this Poisson's equation, we can able to find out the width of the depletion region of a p-n junction diode also. Okay, fine. Next, so coming to this one, BJT, FET, SCR and tunnel diode. So generally pinch off effect is for the FETs, and the controlled rectification is for the SCR, and the negative resistance will be having for the tunnel diode. That's why we are using this one for the microwave oscillations, and the punch through effect will be for the BJT. Okay, punch through effect or else the early effect. Okay, all these things the BJT. So what is the correct option, guys? A to 4. Only one option is there, A to 4. Okay, B to 1 and C to 2 and D to 3. Okay, guys. So it is the option C is the correct one. Okay, guys, fine. So whatever the questions are there, the rest of the questions we will say tomorrow again the same time, 3 to 3:30 in the same YouTube channel. Okay, we will meet tomorrow, guys. So thank you very much for participating, and just try to note down the concepts whatever you feel new. Okay, and before ending the session, the crash course is going to start from October 1st onwards for this 5th November 2020 exam. So please share this information to your friends or colleagues who are planning to write the UGC NET November 5 2020 exam. Okay, guys. So thank you very much, and we will meet in the tomorrow session, guys.